Hey, welcome back. We're going to continue our discussion on how we can use polars with multivariable. And we're going to revisit a problem that we saw in calculus last year where we want to find the area of a rose. Now this rose has three petals. We can tell by the 3 in front of the theta. So this is a 3-petal rose. And because it's with cosine, that first petal is going to be centered on the x-axis, so it's going to be symmetric about the x-axis. We'll talk about that again in just a few moments. Recall we can find the area of one petal and then multiply it by the number of petals. So we never really find the area of the whole thing. We just really find the area of one petal, and because of symmetry, we just multiply it by 3. So to draw the one petal back last year, we said we can let the radius equal 0. If we let the radius equal 0, we get 3 cosine 3 theta. Now the reason we let the radius be 0 because this is where a petal starts and finishes when we're at the pole. Because remember, when the radius is 0, we're at the center of a pole in a polar graph. Solving this then, we're going to get cosine 3 theta equals 0, and I just have to think where cosine is equal to 0, and that is negative pi over 2, pi over 2. Now I'm going to start with negative because I know it's going to be centered in the x-axis for cosine. For sine, I don't have to start with the negative ones. The next one, 3 pi over 2, 5 pi over 2, 7 pi over 2, and 9 pi over 2, and we can keep going. If I divide by 3, we're going to get negative pi over 6, pi over 6, 3 pi over 6, which is just pi over 2, 5 pi over 6, 7 pi over 6, and 9 pi over 2, which is just 3 pi over 2, right there. So what we want is we want to get the petals. The petals, well, we can pick any two of these combinations to get our petal. For example, this would be our first petal, this would be our second petal, and this would be our third petal. So if I were to graph it from last year, starting at 0, at negative pi over 6, I know my radius is 0, and at the angle of pi over 6, I also know that my radius is 0. So between negative pi over 6 and pi over 6, I know my petal has to go out. So it's going to look kind of like this. And I can do the same thing with here. Between pi over 2, my radius is 0. And at 5 pi over 6, my radius is 0. So I know that I have another petal coming out over here. And then I got, of course, 7 pi over 6 and 3 pi over 2. And I can draw my third petal. The world's ugliest looking rose. But it's Valentine's weekend right now, so hey, somebody might like that. We'll make it red just to spice it all up. There we go. And what we're looking for is the area of this rose. So we are going to restrict the domain. So we are going to use polars here. So to get my limits, or my domain here, to get my limits, I'm going to need the change in radius and the change in theta. Well, the radius is simple. The radius is going to go out from here, starting at a radius of 0, and moving all the way out until it hits a maximum radius of 3. I know it's 3 because of my function right there. The biggest cosine could be is 1, so therefore the biggest my radius could be is 3. So to get our radius, we're starting at 0. And to get the radius, the biggest it could be is 3, but still careful. But the radius is changing throughout. So the radius is actually going all the way to the function itself. Which is 3 cosine 3 theta. So it's going to be 3 cosine 3 theta. And theta, now be careful, we're going to restrict theta only to one of these petals. So we'll go from negative pi over 6 to positive pi over 6. So to get our area, since we're using polars, so for polars, the change in area is r dr d theta. So my double integral r dr d theta. My change in radius goes from 0 to 3 cosine 3 theta, while theta goes from negative pi over 6 to positive pi over 6. And that will give us our area right there. So be careful. Remember, the radius is what, if I draw here, well, what's the smallest my radius is going to be? Is 0. Well, the largest my radius is going to be at any given time is my function itself. And that's how we got this 3 cosine 3 theta right there. Okay, so let's take a look at number 4 here. We want to find the volume, so now we're talking about volume of a cylinder above the xy plane with a radius of 1 centered at the origin, but the top is defined by this cylinder, this plane right here. So if we think about it, we have a cylindrical base, a circular base. It's going up until it intersects this plane, and we want to find the volume within there. So we're going to start with the base, which we know is a circle. The circle is going to be a base. Whoops. So my base on the xy plane will be a circle with radius 1. So I can get my domain here, or my limits, I guess. My change in radius goes from 0 all the way out. So my radius is always going to be from 0 to 1, where theta, my change in theta is going to go from 0 to 2 pi. So there's my base. Now I got to multiply that by the height. So I already got the area of my base. So the area of my base would be something like area equals my double integral, right? R dr d theta. So there's the area of my base. Now we just have to multiply it by the height. So how do we get the height? So we're going to calculate the volume by hand using double integrals in polar form. So next we're going to get the height. Well, the height is modeled by this equation. If I solve for z, we would get z equals 4 plus x plus 2y. But be careful, this is not polar form. So I can write this in polar form by converting. Polar form deals only with x and y. Only x and y, not z. This is very similar to our cylinder form, okay? So we're going to leave z alone. So in polar form, my z as a function of r and theta this time will be 4 plus r cosine theta plus 2 r sine theta. And now I can write my volume equation. My volume, of course, would equal, let's see here, my double integral, my height, 4 plus r cosine theta plus 2r sine theta, dr d theta. Now, what am I forgetting? I am forgetting my r. I typically like to put that in the front. Don't forget that r. My change in r goes from 0 to 1, and my change in theta goes from 0 to 2 pi. Now I am going to go ahead and distribute the r here, and that's going to give me my integral 0 to 2 pi, 0 to 1. And let's see what this is going to be now. 4r plus r squared cosine theta plus 2r squared sine theta dr d theta. When we integrate with respect to r, we will get 2r squared plus 1/3 r cubed plus 2/3 r cubed sine theta from 0 to 1. That's a 1 there. And we plug this in, we're going to get 2 plus 1/3 cosine theta plus 2/3 sine theta. We don't worry about the 0 because everything just goes to 0. And I'm going to integrate that between 0 and 2 pi d theta. And when we integrate here, be very careful. We are going to get 2 theta plus 1/3 sine theta minus 2/3 cosine theta from 0 to 2 pi. And if we plug this in, plug in 2 pi for theta, that's going to give us 4 pi minus the sine of 2 pi is 0 minus cosine is 1, 2/3 minus, plug in the 0, well that's 0 plus 0, plug in 0 here, minus 2/3. And those 2/3 will cancel, and we're left with 4 pi. How fun is that? Alright, now last one. We want to write a double integral in Cartesian form, and then use your calculator to compare answers. Alright, so in Cartesian form, what would this look like? Well, if I start off with my unit circle, this is negative 1 minus x squared. This is positive square root of 1 minus x squared. So I know my change in y's are going to go from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And my change in x's goes from negative 1 to 1. So my volume, negative 1 to 1, negative square root of 1 minus x squared, the positive square root of 1 minus x squared. And we're going to put in our heights, because this is going to be dy dx. So my height is going to be the, not square root. It was this function right up here, z plus x plus 4y, plus 2y, sorry. 4 plus x plus 2y. And you would integrate that with your calculator, and you will get 4 pi. So polars are sometimes a little bit easier to solve. This way we don't have to worry about all those darn radicals. So our little drop of hints for you. Are you ready? Our little drop of hints, okay? So these are my big hints for you for areas. Okay? If we're in rectangular form, okay? If we are in rectangular form, ready? The area, the change in area is going to be dy dx. In polar form, the area is r dr d theta. And remember, these are both rectangles. In another video, we showed that this is my arc length, right there. R d theta is my arc length, and that's my radius. And look into the other videos, and you can see that. Or if you go way up here, we kind of showed how that becomes a rectangle, right there. All right. So this is the end of my videos, but if you go to my next video, I am going to go over a couple more about how to write polars using more examples of polars with area, like right up here. Just a few extras for you if you want to take a look.